Most people just see the Golden Gate Bridge as this graceful, static piece of architectural art, but for decades, engineers actually branded it as an impossible project. The main problem was a gap that's about 1.6 kilometers wide, the Golden Gate, a volatile chasm separating San Francisco from Marin County. To span that distance, they needed a structure stretching over a kilometer, which meant the main span would have to beat the record held by New York City's George Washington Bridge by an additional 2.13 kilometers. With the distance between towers fixed at 4,200 feet, the design was 20% longer than anything that had ever been built. The real tension here wasn't just about the horizontal distance, it was a desperate gamble on whether steel could actually withstand the relentless, churning currents of the Golden Gate Strait. This is the story of how a blueprint for a supposedly impossible dream actually became a physical reality. To really get why this bridge was called impossible, you have to look at the water beneath it. The Golden Gate Channel plunges to a depth of 370 feet, creating this dark, churning abyss that just defies standard foundation techniques. This isn't just some ordinary coastal gap, it's essentially a massive hydrological engine. About 7 trillion liters of water surge through this throat every single day, reversing direction twice with the shifting tides. Now, consider the scale here. The average flow hits 23 million gallons per second, roughly double the volume of the entire Mississippi River system. Standing on the shore, you're witnessing a high-pressure maritime machine. Because of this immense volume, the tidal currents often reach speeds nearing 15 kilometers per hour. Just imagine a liquid wall moving at that speed through a 370-foot deep channel. It's a hostile environment where the engineering standards of the era simply didn't apply. Founded in 1776, San Francisco had grown into a metropolis of over 400,000 residents by the early 20th century. The city's geography was basically a confinement. With a total land area of just 122 square kilometers, it was hemmed in by water on 3 sides. For decades, the only way to get to the rest of the mainland was through a saturated ferry system. This bottleneck created a necessity for a crossing, and that's where Joseph Strauss enters the picture. Strauss was a self-promoter and a tinkerer who absolutely craved the spotlight. He didn't just want to build a bridge, he wanted to create a legacy. When he approached city officials to talk about the proposal, he wasn't just offering a technical solution. Driven by a massive ego, Strauss turned the project into his own personal crusade for immortality. By June 1921, Joseph Strauss presented a design that radically changed the project's direction. While initial projections estimated construction costs at $250 million, Strauss undercut them with a bid of $25 million, a tiny fraction of the price others suggested. But, and this is the part where it gets messy, this lower cost was based on a cumbersome structure based on a bascule bridge, a hybrid design combining cantilever spans and a drawbridge element that critics found aesthetically hideous. To fix the flaws of that initial vision, the engineering team eventually pivoted toward a pure suspension design. This transition allowed for minimal structural weight while maximizing efficiency over the vast expanse. The math required for this shift was monumental, and that fell to Charles Ellis, who earned the nickname the Mad Calculator for his exhaustive, complex computations. Despite his importance, Strauss fired Ellis in 1931, following a bitter feud over the time required to refine the tower designs. The project continued under the guidance of Irving Morrow, an architect hired to refine the visual impact. Morrow introduced those characteristic Art Deco angles and vertical panels, effectively turning an industrial machine into a work of art. January 5, 1933 marked the official groundbreaking for the bridge. This was a project launched in the depths of the Great Depression, when 1 in 4 Americans were unemployed. For the laborers battling the fog and those lethal currents, the construction site was a vital lifeline. A worker like Charlie Hennicle earned roughly $5.50 a day, about $27.50 a week. In an era of 25% unemployment, those wages were a luxury. The structure was no longer just a series of calculations on paper. It had become a physical manifestation of steel and concrete, forged by men who saw this dangerous labor as their only chance at survival. Getting the bridge's immense weight onto the bedrock proved to be the team's first real crucible. The South Tower foundation had to be placed 30 meters underwater on solid bedrock, forcing workers into a constant struggle against the shifting ocean. To get to the site, crews built a steel trestle, but the Pacific was unforgiving. A fog-blinded ship smashed into it, and subsequent storms destroyed the structure twice. Divers had a critical window of opportunity that lasted only 20 minutes during the 4 daily slack tides, a tiny time frame for heavy industrial work in dark, swirling currents. To help the men, engineers designed a 9,000 metric ton concrete fender to act as a defensive shield. Once that was in place, they cleared the seabed using black powder bombs for large-scale underwater blasting, a first in bridge support history. They essentially obliterated the ocean floor. After that, they pumped out 35.2 million liters of water to create a dry workspace. By December 31st, 1934, the South Pier was complete, rising 46 meters tall, with 13.5 meters visible above the waterline, ready to anchor the towers. While the South Pier was a visceral struggle, the North Pier was more of a masterclass in efficiency. This 43,000 metric ton structure rested on a bedrock platform only 6 meters underwater, allowing the engineers to finalize the construction in just 5 months. But the weight of the bridge required substantial anchoring beyond just the towers. Crews excavated over 92,000 cubic meters of earth to form massive concrete blocks. To stop the ocean from eroding these foundations, the team used high silica concrete for the first time in history, a precise chemical decision to shield the structures from salt corrosion. The bridge, in essence, is not just a steel span. It's an enormous accumulation of stone and chemistry, locked in a perpetual stalemate with the Pacific. Once the piers were set, the towers began to rise, but they weren't solid blocks of steel. To handle the weight and wind, engineers used a honeycomb design, a series of cellular steel chambers that gave them immense strength without the dead weight of solid metal. Each tower required roughly 600,000 red-hot rivets to be driven into place, a process that filled the air with a deafening rhythmic metallic clatter. However, this architectural triumph hid a toxic secret. Inside those narrow, unventilated honeycomb cells, workers were exposed to concentrated lead fumes from the painting and welding processes. While the bridge grew taller, the men inside the cells were breathing in a silent poison, trading their long-term health for the speed of construction. This contrast between the external beauty of the Art Deco spires and the internal toxicity of the cells defines the brutal industrial reality of the project. Working hundreds of feet above the churning strait, the risk of death was a constant. Joseph Strauss, unlike many of his contemporaries, insisted on a safety net beneath the floor of the bridge. This was a massive, expensive mesh of hemp and steel that cost $130,000, a staggering sum at the time. This net didn't just save lives, it created a legend, the Halfway to Hell Club. These were the 19 men who plummeted through the air, experiencing the terrifying sensation of a freefall before being snapped back by the mesh. While the net was a triumph, the project's safety record remained imperfect. 10 men eventually died during construction, including a tragic accident where a section of scaffold fell through the net, taking several workers with it. The net saved many, but it couldn't eliminate the inherent lethality of the environment. With the towers complete, the final act was the spinning of the main cables. This wasn't a process of hanging pre-made ropes, but a mechanical ballet of wire. Using the Roebling method, spinning wheels traveled back and forth across the span, carrying individual strands of galvanized steel wire. To create the 2 main cables, workers spun 80,000 miles of wire, enough to circle the Earth more than 3 times. Each cable consists of 27,572 individual wires bundled together and compressed into a single massive cylinder. Now, imagine the tension here. These cables are the hammock that carries the entire weight of the bridge deck. The sheer scale of this operation meant that if the cables were to snap, the energy released would be equivalent to a small explosion. The precision required to keep those thousands of wires parallel and perfectly tensioned was a feat of mathematical discipline that turned a chaotic mass of steel into a singular load-bearing artery. This steel hammock now serves as a permanent, iconic feature of the California coast, but its foundation remains anchored in notoriously unstable ground. The city it serves has endured seismic events that engineers had to carefully consider, most notably the earthquake of April 1906, which obliterated 28,000 buildings, ruptured gas lines, and ignited citywide infernos. When observing the Golden Gate Bridge today, you see a testament to industrial resilience. It stands against the unrelenting pressure of 7 trillion liters of daily tidal flow and the constant degradation of salt-laden air. The facts demonstrate that the bridge is less a static monument than a triumph of survival against a hostile environment. As the tides continue to churn beneath the South Pier, one has to ask, how many more decades will this engineering logic hold against the Pacific's inexorable pressure?